Hello students, good morning to all of you. 1 week ago, we studied different articles in the topic coordination compounds. So in the coordination compounds, first of all we studied the definition of coordination compounds, then classification of complexes, then after that we studied IUPAC nomenclature system for coordination compounds, then effective atomic number rule, then isomerism in coordination compounds, and in the last video we studied structural isomers, then stability of coordination compound and factors which governs the stability of complexes. So after studying factors which governs stability of complexes, today we are going to study the next article in this topic. That article is theories of bonding in complexes. So theories of bonding in complexes, which we are going to study today. So Werner was the first scientist to explain bonding features in coordination compounds. So bonding in coordination compounds was first of all explained by scientist Werner. But theory cannot explain. Werner's theory cannot explain basic questions like why only certain elements possesses property of forming coordination compounds, or why bonds in coordination compounds have directional properties, or why coordination compound have characteristic magnetic and optical properties. So answer of such questions was not given by Werner's theory. That means in short, Werner's theory cannot explain some concepts. Therefore, there are different theories which can explain. There are many theories which can explain nature of bonding as well as properties of coordination compounds. So there are many theories which can explain nature of bonding, nature of bonding, nature of bonding as well as various properties. As well as various properties. Various properties of coordination compounds. Of coordination compounds. So these theories are, first one, it is the valence bond theory, that is VBT. Then second theory, it is crystal field theory, CFT, crystal field theory. Then there is also third theory which can explain bonding in complexes, and that theory is ligand field theory. Ligand field theory. Or there is one more theory which can also explain bonding and properties of coordination compounds, and that theory is molecular orbital theory, MOT. So according to our syllabus, we are going to study only valence bond theory and crystal field theory. So these theories, they explain bonding in coordination compounds and properties of coordination compounds or complexes. So among these theories, we are going to study valence bond theory and only crystal field theory. So let's study the first theory, that is valence bond theory. So VBT, in short it is called as VBT. So it assumes that bond formed between metal ion and ligands. It assumes that the bond formed between metal ion and ligands are purely covalent coordinate. Are purely covalent coordinate or coordinate bond, or it is also called as dative bond. So VBT theory, it assumes that bond formed between metal ion and ligand are purely covalent coordinate. That means coordinate bond is present in coordination compounds or coordination complexes. So different steps involved in describing bonding in coordination compounds using valence bond theory are as follows. So bonding in coordination compounds using valence bond theory, it involves following steps. So let's study these steps one by one. So the first step is metal ion. Metal ion provides vacant orbitals. Metal ion provides vacant orbitals, and these orbitals, they may be s orbital, they may be p orbital, and they may be d orbital. So metal ion provides vacant orbitals like s orbital, p orbital, and d orbitals of metal ion for for formation of for formation of formation of coordinate bond, for the formation of coordination bond, for the formation of coordination bond with ligands. So the first step we studied here is metal ion provides vacant orbitals like s orbital, p orbital, d orbital for the formation of coordinate or coordination bond with ligand. To form the bond with ligand, metal provides vacant orbitals like s, p, and d. Then the second step is vacant d orbital. Vacant d orbital. So vacant d orbital along with other orbitals like s orbital and p orbitals, s orbitals and p orbitals of metal ion takes part in hybridization. Takes part in hybridization. So during the formation of coordination compound, vacant d orbital along with s and p orbital of metal ion takes parts in the hybridization. In the process of hybridization, d orbital along with s orbital or p orbital they takes part. Then the third step is the number of vacant hybrid orbitals. The number of vacant hybrid orbitals formed is is equal to. So during the formation of coordination bond between metal and ligand, number of vacant hybrid orbitals formed is equal to. Number of vacant hybrid orbitals formed is equal to the number of ligand donor atoms. The number of is equal to the number of ligand, the number of ligand donor atoms, number of ligand donor atoms surrounding the metal ion, surrounding the metal ion, surrounding the metal ion, surrounding the metal ion, which equals to, which equals to which equals to coordination number of metal, which equals to coordination number of metal, coordination number of metal. See here once again, third step is the number of vacant hybrid orbitals formed, it is equal to number of ligand donor atoms surrounding metal ion, which equals to coordination number of metal. So we studied about the coordination number previously. So coordination number is nothing but the number of ligands, the number of ligand donor atoms, that is the coordination number. So to understand this, take one example. So in complex CuNH3 4 times SO4. For example, take this complex. So in this complex, Cu2 plus ion provides 4 vacant orbitals, provides 4 vacant orbitals, 4 vacant orbitals. So in the complex CuNH3 4SO4, here Cu2 plus ion is present, and that Cu2 plus ion, it provides 4 vacant orbitals. The number of vacant orbitals form is equal to the number of ligand donor atoms surrounding the metal ion, which equals to coordination number of metal. So here in this complex, Cu2 plus ion provides. So here 4 NH3 ligands are present around the Cu2 plus ion. Therefore, Cu2 plus ion provides 4 vacant orbitals. Why 4 vacant orbitals? Because here Cu is surrounded by 4 ammonia molecules. These are the ligands. 4 ligands. That's why Cu2 plus ion provides 4 vacant orbitals. Then the next step is overlap between vacant hybrid orbitals. Overlap between vacant hybrid orbital of metal and filled orbital of ligand leads to formation of leads to formation of metal ligand coordinate bond. Metal ligand coordinate bond. So overlap between vacant hybrid orbital of metal. Overlapping means mixing of orbital. So overlap between vacant hybrid orbital of metal and filled orbital of ligand. Overlapping, that is mixing of orbital between vacant hybrid orbitals of metal, mixing of vacant hybrid orbital of metal and filled orbital of ligand, it leads to formation of metal ligand coordinate bond. So due to overlapping between hybrid orbital of metal and filled orbital of ligand, there is the formation of metal ligand coordinate bond. Then the next step is the hybrid orbitals used by metal ion points in the direction of ligands. That is about the geometry of complex. The reason behind the geometry of complex is the hybrid orbitals used by metal ion, it points in the direction of ligand. That's why complex having a specific geometry. Then the next step is n-1d or nd orbitals used in the hybridization. n-1d and nd orbitals used in hybridization allow the complex to be classified as. So during the complex formation, n-1d orbital and nd orbitals are taking part, and due to this, complex can be classified into two types. So the first type is outer orbital complex. Outer orbital complex. So the first one, it is the outer orbital complex, and Second one is opposite to that. Second, that is B, inner orbital complex. Second one is inner orbital complex. So n minus 1d and nd orbitals used in the hybridization allows the complex to be classified as outer orbital complex and inner orbital complex. Complex can be divided as or classified as outer orbital complex and inner orbital complex on the basis of which orbital it is used in the hybridization. So, for hybridization in outer orbital complex, for hybridization in outer orbital complex, ND orbitals are used. For hybridization in outer orbital complex, ND orbitals are used. Whereas in inner orbital complexes, n minus 1d orbitals are used. N minus 1d orbitals are used. So n minus 1d and nd orbitals which are used in hybridization allows the complex to classified as outer orbital complex and inner orbital complex. So for hybridization in outer orbital complex, which orbitals are used? ND orbitals are used. Whereas for hybridization of inner orbital complex, which orbitals are used? N minus 1d orbitals are used. Thus, inner orbital complex or inner orbital compound and outer orbital compound or complex and inner orbital complex or compact compounds can be defined as, so the first one, it is the inner orbital complex or inner orbital compound. So metal atom that uses inner shell d orbitals for the hybridization of central metal atom. So inner orbital complex or compound is metal ion that uses inner shell d orbitals, and outer orbital complex is the compound or complex in which metal atom that uses outer shell of d orbitals, for hybridization of central metal atom. So in inner orbital complex, inner shell d orbitals are used, and in outer orbital complex, here which d orbitals are used? Outer d orbitals are used for the hybridization. Then the next one is types of hybridization of metal orbital describes or decides structure of complex. So before studying this, once again I am going to repeat the last step in the valence bond theory. So for hybridization in outer orbital complex, N-d orbitals are used. Whereas in inner orbital complex, which orbital is used? N-1 orbitals are used. So type of hybridization of metal orbital. Type of hybridization of metal orbitals describes or decides. Type of hybridization of metal. It decides structure of complex. Structure of complex. It is decided by the types of hybridization of metal orbitals. To understand this, let's take some examples. So when hybridization is sp, type of hybridization of metal orbital that decides the structure. So when in a complex hybridization is sp, when hybridization is sp, at that time structure of complex is a linear. Type of hybridization it decides. Type of hybridization it decides the structure of complex. So when in a complex hybridization is of sp type, then structure is linear. When hybridization in a complex is sp3, when hybridization in a complex is sp3, the structure is tetrahedral. Structure is tetrahedral. So when hybridization is sp3, structure is a tetrahedral. Or when in a complex hybridization is dsp2, hybridization is dsp2, then structure is a square planar. Structure is a square planar. On the other hand, when hybridization is d2sp3, when hybridization in a complex is d2sp3, then the structure is octahedral. Structure is octahedral. So you please remember all these types of hybridization and shapes. Once again, I am going to repeat this. So type of hybridization of metal orbitals. Type of hybridization of metal orbitals. It describes or it decides the structure of complex. Where in a complex type of hybridization is sp, then structure is linear. Where in a complex hybridization is sp3 type, then structure is tetrahedral. When hybridization is dsp2, then geometry or structure is square planar. And when hybridization is d2sp3, then structure is octahedral. So for MCQ, you please remember the type of hybridization and different structure or geometry of complex. So you please concentrate upon this to solve MCQ type of questions. Then the next article which we are going to study is steps to understand metal ligand bonding. Step to understand metal ligand bonding. So here let's study the different steps to understand metal ligand bonding. So the first step First step is find oxidation state of central metal ion. Find oxidation state. Find the oxidation state. Find the oxidation state of central metal ion. Of central metal ion. Central metal ion. So oxidation state, first of all we have to find out. So to understand metal ligand bonding, first step is we have to find out oxidation state of central metal ion. We know that oxidation state, it is also called as oxidation number, or in short oxidation state is degree of oxidation. So total number of electrons that an atom either gains or loses in order to form covalent bond is the oxidation state. So first of all we have to find out the oxidation state of central metal ion to understand metal ligand bonding. Then to understand metal ligand bonding, second one is write valence shell electronic configuration of metal ion. Write valence shell electronic configuration of metal or metal ion. So second step is write the valence shell electronic configuration, that is outermost electronic configuration of metal ion. This is the second step. Then third step is see whether complex is. Third step, see whether complex is low spin or high spin. See whether complex is low spin or high spin. Third one is see whether complex is low spin or high spin. So low spin complexes are nothing but complexes in which there are paired electrons. Low spin complexes are nothing but the complexes in which there are paired electrons, while high spin complexes they contains unpaired electron. So low spin complexes mean complexes in which electrons are paired, and high spin complexes are nothing but complexes which contains unpaired electron. So third step is see whether complex is low spin complex or high spin complex. Then next step is from number of ligands find the number of metal ion orbital required for bonding. Metal ion orbital. From number of ligands find number of metal ion orbitals. Metal ion orbitals. Metal ion orbitals required for bonding, required for bonding, required for bonding. So from the number of ligands, find the number of metal ion orbitals required for bonding. This is the next step. Then the fifth step is identify orbitals of metal ion available for. Identify the orbitals of metal ion available for hybridization. Available for hybridization. Available for hybridization and type of hybridization involved. And type of hybridization. And type of hybridization involved. Type of hybridization involved. See once again. So identify orbitals of metal ion which are available for hybridization. We have to identify orbitals of metal ion which are available for hybridization and type of hybridization involved in it. Then the next step is write electronic configuration. Write electronic configuration after hybridization. Write the electronic configuration after hybridization. We have to write the electronic configuration after hybridization. This is the next step. The next step is show the filling of. Next step is show filling of orbitals after complex formation. Show the filling of orbitals after complex formation. After complex formation. Listen once again. Next step, write electronic configuration after hybridization. Then next one, it is show the filling of orbitals after complex formation. We have to show filling of orbitals after the complex formation. And last step to understand metal ligand bonding is determine the number of unpaired electron and predict magnetic behavior of complex. In short, I am going to represent here. Determine the number of unpaired electron. Determine the number of unpaired electron. Determine the number of unpaired electron. So determine the number of unpaired electron and from this predict magnetic behavior of complex. Predict the magnetic behavior. Predict the magnetic behavior of complex. So last step is determine number of unpaired electron and from number of unpaired electron determine the magnetic behavior of complex. Magnetic behavior of complex means it is diamagnetic or it is paramagnetic. That we have to decide from number of unpaired electron. So here we finished different steps to understand the metal ligand bonding. Once again, we are going to repeat all these steps. So to understand metal ligand bond, the first step necessary is we have to find oxidation state of central metal ion. So to understand metal ligand bonding, first of all, find out the oxidation state of central metal ion. Then next, write the valence shell electronic configuration, that is outermost shell electronic configuration of metal ion. After that, after finding out oxidation state, then we have to write the valence shell electronic configuration of metal ion. Then after that, see whether complex is low spin complex or high spin complex. So low spin complex means when all electrons are paired, that is a low spin complex, and when unpaired electrons are present, that is the high spin complex. So after writing valence shell electronic configuration, then we have to decide whether complex is low spin complex or high spin complex. The next one, from number of ligands, find the number of metal ion orbitals required for bonding. From the number of ligands, find the number of metal ion orbitals. The next one is identify orbitals of metal ion available for hybridization and type of hybridization involved. So identify orbitals of metal ion available for hybridization. So which orbitals are available for hybridization, that we have to identify, and now we have to identify also the type of hybridization involved in the complex formation. The next one is write the electronic configuration after hybridization. Then after that, next step is show filling of orbitals after complex formation, and last step is from the number of unpaired electron determine the magnetic behavior of complex, whether complex is paramagnetic, diamagnetic. We can decide it from the number of unpaired electrons. So thus today we completed two articles in this topic. The first article is valence bond theory, and next article which we studied is steps to understand metal ligand bonding. So once again I am going to repeat the articles which we studied in short. So bonding in a complex, it can be explained by various theories. So Werner was the first scientist to explain the bonding in coordination compounds. But Werner theory, it cannot give answer to some questions. That's why to explain bonding in coordination compounds, different theories are used. First one, it is the valence bond theory. Second one is crystal field theory. Then ligand field theory and molecular orbital theory. So let's study the first theory, that is valence bond theory, that is VBT. So VBT, it assumes that bond formed between metal ion and ligand are purely covalent coordinate. According to valence bond theory, the bond between metal ion and ligand is purely covalent coordinate. Then we studied the different steps from first to 7. We studied different steps involved in the valence bond theory. After that, we studied type of hybridization and structure. So structure of a complex, it depends upon the type of hybridization. For example, if complex having sp hybridization, then that complex having the structure linear. Or if hybridization involved in the complex is D2sp3, at that time the structure or geometry of complex is octahedral. Then last article was steps to understand metal ligand bonding. Different steps we studied to understand the metal ligand bonding. So here today we are going to stop here. Thank you.